Today we're going to be reading Conveyor, a one-tool-fits-all continuous software deployment at Meta from the abstract. It seems like they use the system to do two things. They do continuous deployment, which is they deploy the changes as they are submitted into the code base. And then they also do deployment on a fixed schedule. And they talk about Conveyor, how Conveyor handles that, those two types of deployment. And also they talk about some novel things that Conveyor does, including, but not limited to, deploying ML models at scale and a few things related to capacity changes. So let's jump into it. Okay. So they're talking about containers. I'm actually curious what their container system is. I can't remember which container system they use. Do they use Kubernetes? Maybe we will find out in a future part of the paper. But I think it's actually more likely to be in the cluster manager paper that they have. Okay, I want to make sure this is centered and people can see it. Okay, so okay, so they say out of all deployment pipelines for services deployed via containers, 97% of them have fully automated deployments. They also have continuous deployment, and they have fixed schedule deployment. And then they talk about several distinguishing features of Conveyor, including safe in-place updates to reduce hardware costs. I'm curious what this means. Curious how they have safe in-place updates. I'm curious how they have analysis of code dependencies to prevent faulty releases. Okay, so maybe this is static analysis. And the capability to deploy complex ML models at scale. So that's interesting. Release early, release often. Front fast, serverless. So they have their own serverless function as a service. Wow. Tens of thousands of developers are making changes to the function as a service platform itself. That's interesting. That's interesting. I'm wondering why they're making changes to the platform itself versus having some sharded way of rolling out changes, because my interpretation is that tens of thousands of developers would actually be writing code that is related to the functions themselves, not necessarily the actual platform code base. So that's interesting that that's the way that they choose to do it. I would imagine that, another alternative would be to have some shared front FAS, and then there's some common code, and then each of the functions is deployed separately, which seems a bit safer, but maybe a bit more complicated. I'm curious why it is this way, but maybe they talk about front FAS. So, sorry, let me take my notes. So, front FAS is big. It's a big service. Big is a big service. It's like Lambda or the GCP equivalent. Interesting that developers are making changes to the core platform. Yeah. And what is this that they reference? 33. Rapid release at massive scale. Okay, cool. I definitely want to read that. So... Okay. So they're answering 3 questions. So the 3 questions are, what is the adoption rate of deployment automation, and what is important in driving the adoption? What is special about deployment safety at hyperscale, and what distinguishes the deployment of ML models from traditional service executables? Okay. Okay. Okay, cool. I'm curious what... Oh, this is such a cool paper. Automated deployment, so cool. And I think is very... It's definitely related to my interests because in my day job, I am interested in site reliability. So I think this is really cool that they're talking about how they have all these safety features. So they talk about advanced safety features. Okay. So yes, it supports 2 types of deployments: fully automated continuous deployment Okay. To automate deployments, bugs and deployment failures must be embraced as a norm. Okay. Automated guardrails, such as testing and health checks. Only less than 1% of finished deployments are manually averted or patched by developers. Okay. But how many outages happened? How many outages happened? So, this is still the introduction. So adoption of deployment. So deployment safety at scale. So they want to make in-place updates safe. Okay, what is the definition of an in-place update? So basically, I think the answer to the first question is they've managed to get most services to use it. And the introduction of automated tests prevents higher rates of rollback. Okay. Okay. So they are going to, so rather than keeping old deployments around, they update the tasks on machines, and they've changed the cluster manager that they have, which I believe is called Twine, to accommodate this idea. Okay, I haven't read the Twine paper, so I don't know what this is. They also talk about health checks on moving targets. I don't understand what this is. Hopefully they talk about it more in the paper. And okay. Okay, cool. So they have some, basically, being able to mark deployments that are known bad as not deployable is good. So great. Now they're talking about ML model deployments. Okay. So I actually have the least experience with ML model deployment, but I think this will be very interesting because I wonder if what their practice is widely accepted by the industry as being the best. Let's check on the chat, and let's also check on the, what's it called? Oh, I should also post the link to the thing in the chat. We're reading conveyor, which is one size. Okay. So their contributions, we make several contributions. So they're talking about their production experience. They're talking about data on why this approach of deploying so often is actually feasible. Learning from production experience. We have data on why advanced or aggressive deployment strategies are okay. And then they talk about some safety features. Okay, so now we're gonna go to, this is the intro. have the overview okay. We've got deployment scenarios and solutions. A lot of deployment scenarios and solutions, very interesting. The case study of front FAS. Design and implementation of conveyor. Then we've got evaluation production. I always love this from the meta papers. They always have very interesting evaluation production. Big scale. It's amazing. Then what else do we have? Related work. Okay, so they talk about deployment tools such as Spinnaker or CodeDeploy, AWS, Azure stuff. Google has some stuff, Circle CI. They talk about cluster managers and Protean from Azure. Actually, that is one that I didn't know. I wonder, yeah, I had never heard of Protean before. So they've also talked about some new challenges, and that's interesting. Okay, so conclusion. We presented the deployment scenarios, operational experience, and production data related to software deployment at Meta, along with the design and implementation of Conveyor. We demonstrated the feasibility of frequent and fully automated deployments supported by a single deployment tool. And they talked about some of the novel things that they did. Cool. That all makes sense to me. Now let's read some of the references. They talked about this one, a declarative approach for updating microservices, which seems interesting. They talk about Buck, which was the Twitter.com thing. Oh wow. It was the Twitter.com thing, I believe. What else? Continues to deliver with Spinnaker. I have not heard of this Spinnaker. It's an open source thing. Oh, cool. Automatic feedback directed optimization. What else do we have? Protean. I had not read this paper. It's from 2020. This is another paper that I haven't read, but I can't just read meta papers, but this is another one that I could read. Shard Manager I've read and written about on michaelleonard.com. This is also very interesting. Gandalf, it's some automated detection of services that are, or if the service is causing a problem. Autonomous testing. Autopilot. Very cool. Service router, read that previously. Spinnaker rollout strategy. Holistic configuration management at Facebook. I'm thinking that maybe I should do a series where I just read about cluster managers. There would be Twine, there would be Protean, there would be Borg. Could be interesting. Borg. Okay, that's it. Okay, so now we're going to go read the rest of the paper. I'm actually going to grab some water and then we will be right back. All right, we are back, and now I must check whether my audio is still working. We're back, and now I must check whether my audio is still working. It is still working. That is great. Okay, so now let's talk about the deployment culture. Overview of software deployment at Meta. Okay, so they talk about why they mandate So there's a mandate for software deployments. Frequent releases, enhanced developer productivity. They have A/B test results. So faster feedback on the changes. e.g. A/B test results. Okay. Releases have fewer changes, making it easier to debug any problems. Right. So basically, timely deployment. Wow, Facebook didn't deploy for 2 months? That's wild. 2014? In 2014, they didn't deploy for 2 months? Wow, that is unbelievable. I have a hard time believing that. How is that possible? Because Facebook in 2014 was already super huge. So that's wild to me. Okay. Then we have, okay. So basically, they have some automated system that notifies you if you're not complying with the mandate of deploying. Okay, they have microservices, and a service has one or more jobs, and the jobs have tasks, and a task actually maps to a Linux container. Maybe they actually are just using straight up Linux containers and not any other container thing. Yeah, related to my question earlier. I could see that. That would make sense. So, okay. Okay, so this is how they have a DAG. They have a DAG of inputs, which are artifacts, and actions to take. Excuse me. Excuse me. Wow. So they have a simple DAG in figure 1. Okay. And they have a more complex one in figure 3. Artifacts are source code and compiled executables. Once all the input artifacts of a pipeline are ready, the pipeline will be executed, creating a release. Okay, so let's see what is in this DAG. You got the code, then you build it, then you create an image, and then you deploy it. Okay, cool. And there is also some other stuff that is involved. You have conveyor, you have this config management system, you have some service that is actually health checking, so checking to see whether the new tasks or the new containers are performing well. And then you have a task controller, which we will learn more about. Okay, great. So one of the things they're talking about is staged rollouts by deployment phases. I think this is talked about in the S3 book, but basically you do not update all the tasks at once, because what happens if there's a bug in all the tasks? Then everybody would be exposed to the bug. So you update a small number of tasks, and then if the small number of tasks has a problem, then you can stop or roll back, and then fewer people are impacted by the problem. To check service health, Twine and the service itself can log various health signals such as CPU utilization and user engagement metrics. The health check service is responsible for checking these health signals for anomalies based on user-defined rules. For example, it can detect if user engagement drops below a certain threshold. Collecting health signals often requires a waiting period to gather monitoring data, known as the bake time. Okay. In addition to driving Twine to deploy service executables, Conveyor can also drive Configurator. Okay. I think I've heard about Configurator before, and this is for phase deployments of ML models. Okay, and you can also limits the blast radius. and the service are health checked based on CPU utilization and user engagement metrics. Okay. And then services can have their own task controller if they want. Okay. So we illustrate the interaction between various components in Figure 1 through the example of deploying a new software version for a sharded key value store, KV store. Okay. Okay. They're talking about a quorum protocol. So basically you have a group of servers need to agree on a value, and if you have 3 replicas but only one of them is up, then how can you agree? It's impossible to have a majority of the replicas agree, because one third is not a majority. Okay. Okay, so they're talking about for the task controller key value store, which has tasks that could be from the same replica, or it could be a replica of the same data. Okay. Okay. Okay, so there's some communication between the cluster manager and the task controller to negotiate which tasks are actually updated. Okay. Okay, there's some health check, user engagement metrics, error rate. It's interesting that the metrics that they choose to health check on: error rate, latency, and user engagement metrics. Okay. Okay. Separation of concerns is a key principle. Okay. Okay, great. So they're basically separating out the idea of it is safe to update these tasks from the actual updating of the tasks. Okay. Okay, so then to achieve universal coverage, Conveyor supports a wide range of deployment scenarios. Okay. Yes, this is very interesting because we know that Meta is actually very interested in hardware costs, because from the paper from Service Router, they talk about how if they had a sidecar, which is a potentially different implementation of the idea of how do you route traffic from X service to Y service, basically by having a proxy, it uses more resources. And they talk about how much resources it actually uses. So efficiency. And there are basically in-place updates versus mirroring approach. And the mirroring approach uses more resources. Okay. Yep. Okay. Understand this. This is interesting. The in-place update approach lacks widespread support from existing deployment tools due to the difficulty of ensuring deployment safety. I'm curious why existing deployment tools lack this. Is it because the existing deployment tools are not monitoring the tasks in the same way? That would be my guess. Okay. Okay. So they basically have two in each phase. In each phase, they update small numbers of tasks with really basic checks, and then the health checks are more comprehensive. Okay, I really like that they are talking about the different designs for the system. Different potential designs. I want to make sure my audio is still working. Okay. So let's consider small. If Conveyor instructs Twine to update n small tasks instead of n big tasks, and then waits for a period of time to collect comprehensive health signals, the deployment speed would be too slow. Okay. Okay. So they're talking about a limitation of Kubernetes, which is interesting. I don't really know what this is talking about. So let's come back to this. Okay. Okay. So they're talking about, well, if you need precise control over which tasks are updated, then you have this task control. And they talk about previous work. Okay. Okay, so there is some Twine won't update so many tasks. Won't update so many tasks in order to prevent loss, insufficient live tasks, basically. So basically, it sounds like if Twine detects that updating the task is going to cause a service to go below its budget of the number of tasks that can be offline, then it will stop. Okay. Oh, that's pretty cool. So, zero downtime hot swap. Very cool. With eBPF. So, I wonder what they're linking to. eBPF. Oh, they just linked to the eBPF page. Okay. Cool. Okay, so then they're saying, okay, summary of all of this, all of the in-place updates is that existing cluster managers don't provide these functions because there needs to be tight control between cluster manager and deployment tool. It's very interesting to me. I wonder if it's some fundamental constraint of Kubernetes, because I know that there are open source deployment tools. So could they not be updated to do this? Okay, anyways. So now they talk about deployment safety. Okay. So there's moving target health checks. This is what I didn't understand earlier. After each deployment phase, Conveyor invokes the health check service to evaluate the health of the service. Application level business metrics, RPC metrics, system metrics. Very interesting. And then they talk about the different types of thresholds that can be set. This is very interesting. Multiple types of metrics and multiple types of thresholds that can be set. Okay, so basically you're just checking the version. Health checking service. Differentiating between tasks with new and old identifiers and comparing them. Okay. Okay, bad package detector seems pretty straightforward. Yeah, that seems pretty cool. Stops, rollouts, if they are of that has a version with some bad changes. 14% of to be deployed. That's pretty cool. But it seems very high. Ooh. Okay. Okay. They have testing. Testing checks performance and tests interactions between services. Okay. Okay, cool. Okay, great. So they talk about why they need moving targets. It's because you want to be looking at the right things, the right tasks. Okay, so now we have ML model deployment. Okay. Okay. Okay, that's cool. So ML model deployment, deploy configuration separately from the model binary. Saves on startup cost, e.g. So this saves on startup cost, e.g. loading up data from array. talk about owl. To do, learn about owl. Okay. Okay, so they've addressed concerns about incompatibilities between different parts of the model serving infrastructure. Okay. Okay, so they're basically models depend on each other. So there's a system for coordinating model deployments, and also randomizing the deployment if it's possible. When updating an ML model without modifying the executable, only the corresponding child pipeline is executed. Okay. Okay, advanced features for universal adoption. So okay. Okay, so there are more advanced conditions in the DAG. Mutable artifacts. That's super cool. For example, automating so that's very cool. So they basically have some system that automates feedback-driven optimization as part of the deployment. So basically directed optimization is a process by which you gather production data and then use that to optimize your binary. So being able to go back and change the binary and then update it, or figuring out what actually needs to be optimized, and then using that seems useful. Yeah. So, cool. So for things, CLI and daemons that are deployed everywhere, are able to take advantage of async updates, basically. Okay. Okay, so then they have some system for backwards compatibility, which actually seems somewhat standard. Software backward compatibility. Introduce a new API and gradually move to it, and then perform for DB migrations, perform double writes. Yeah. Okay, cool. So now the summary of distinguishing features. And then we're going to get the case study, which I think will be, the case study. And we haven't even gotten to the design and implementation yet. Wow. Wild. Okay, so they talk about some of these distinguishing features, in-place updates, we know that. Task control, so you can control how the speed and sequence of task updates. The ability to update a subset of tasks, so moving targets. Then they have the thing about if a release is going to have bad code, don't roll it out. You have ML model deployments, and then you also have being able to support more custom things, sounds like. Okay. And then basically they argue that these features make Conveyor able to be adopted in Meta. All right. That's cool. Since there's some feature that wasn't supported, so the ML inference platform changed their architecture. Okay, now we're going to learn about the case study of front fast. I feel like I probably will not write as much about this. It's more going to be reading. So, serverless function as a service. Only hosts event-driven async functions. Sorry, it only hosts synchronous functions, while event-driven async functions are hosted by another platform. Okay, this is actually what I was confused about. So they are writing the serverless function code, not the actual platform level thing. Okay. Okay. Cool. Okay, so they have some filter to filter out tasks that are machines that are going to be load tested. Okay, then they have some custom stuff to actually pull the container image to machines. Okay. Okay, that's cool. So they're basically updating the tasks based on what the predicted blast radius is. It's kind of funny because it's kind of going back to the idea of why did engineers used to work at night? It's because people weren't using the machines, so you could run your code really fast. So it's kind of like, well, if you want to deploy something really fast and see how it does in production, you can do it at night at Meta if you're writing these PHP functions. Okay, so now we learn a bit about how conveyor works, and then we're going to do the evaluation production. Actually, this is the design implementation is pretty short. So the architecture, stateless services, the shared database. Okay. The database stores a bunch of stuff, user-defined pipelines, as well as the last step. There are many shards. All components of conveyor adhere to the worker pool paradigm. Okay. Cool. So, interesting. So let's see what they do. Each pipeline accepts a set of input artifacts. The release creator periodically scans for new input artifacts by invoking artifact finders. When new artifacts are discovered, conveyor creates a release object in the database. Cool. The run scheduler schedules the execution of releases and actions by periodically scanning through all releases and stepping through each action in each release's corresponding pipeline. Okay. Okay, so the run scheduler does some logic about deduping potential releases. Okay. The run manager then initiates the execution of the action. Okay. Okay, cool. There's a extensible architecture. Since the deploy action is the most complex part of conveyor, we describe it in more detail below. I'm actually going to, after finishing this, I'm going to take a quick break. Okay. Okay. So this section is implementation of the deploy action. So it's customizable based on speed and safety, basically. Okay, finally, users have the option to deploy to environments that are not managed by Twine by implementing custom deployment types. Okay. Oh, So, yeah. So you got the custom deployment types allow users to configure how deployments happen. There's a balance between speed and safety. Cool. I will be right back. All right. I think we will get close to finishing up the paper soon. So, great. Wow. Currently, conveyor is implemented in 360,000 lines of Rust. Okay. So, okay. So when conveyor or twine fails, the entire ecosystem cannot update itself. It would be great. It would be great to know more about this. I would love to learn more about this. Maybe it's in the later part of the paper. Huh. So that's interesting. So let's copy this. So in a failure scenario, where conveyor or twine fails, the systems cannot update. But to solve this, they have basically independent instances of twine can independent instances of twine can update the other components of twine, and they have the ability to add more of those independent top level instances. Okay. So this is lessons. V1. Very simple, but 12% of services adopted it. V2, long-running service. Long-running service with scheduled updates, scheduled rollouts. Added extensibility. Complete rewrite from Python to Rust.
More advanced features. Okay. Okay, so however, we will still maintain, so there's still some constraints, including that there was delay in the rollouts. This is now solved by immediate triggering of the next step. Okay, great. Now we get to the exciting part, evaluation and production. And then I think we'll almost be done. So we talk about the constraints, or the questions that they're answering, rather. So has conveyor achieved universal coverage? Do developers trust the automated deployments? Are the safety mechanisms effective? How often do deployments fail, and why do they fail? And what are teams doing with the pipelines? So so that's cool. 44% of the pipelines deploy ML models. That's very cool. So there are 100, looking at of the largest services. Conveyor has 100% coverage. But I'm wondering, like, why these 195 services? Like, how much of the capacity does this actually make? Why not 200 services? Okay. It's kind of yeah, seems fine. But it's a bit hand wavy. I would like to know a bit more about why 195. But cool. So they have most services are using automated deployments, but the ones that aren't have manual checks because the health checks are complicated. Okay, so all the deployments of some services are already fully automated. They still prefer deployments on a fixed schedule over continuous deployment. Yeah. Okay, so it doesn't make sense to deploy every service continuously, e.g. Zookeeper or services that wouldn't have incident response.
Okay, so ensure the safety of in-place updates, Twine's task control. Okay. Okay, so okay, cool. So that's so basically, so like not overloading tasks seems to work. Looking at FAST system. So looking at the FAST system, you can see that there are more task updates at non-peak load. At trough, because you wouldn't overload. Okay, then we also have, so this is task updating rate, and then we also have the executables canceled by the bad packet detector. That's cool. That's wild. One serious bug per day. Very cool. So why do deployments fail? Release failures. So breakdown of release failures, percentage. Oh, by action type. So release failures are caught early at build or deploy steps. That's even before rolling out. I see. But how can people submit code that doesn't pass the unit tests? That's my other question. Okay. Okay, cool. Okay, cool. Oh, this is very cool. So of the failures, what is the of the failures for tasks, many of them, there's a distribution.
there are different reasons. Wow. The rate of false positives is 41%. That seems very high. Even with stringent health checks, it seems quite high. Okay, so figure 9 further presents the point at which a deploy action fails. Got it. That's cool. So deploy actions fail either at small numbers of tasks or at large numbers of tasks. Generally. That's cool. So then pipeline patterns and recommendations. So average number of actions per pipeline. Regular services, 3.5. Large services, 12.2. Okay. Larger services have more intricate pipelines, as expected. Large services are more likely to have canary / perf / integration tests, and also manual decisions. Okay, and then we have deploy action. How long does it take to actually deploy? Okay, so depends on the different strategies. So how long does it take to actually deploy depends on the strategy, and the strategy varies by service type, and also the time spent in deploy actions isn't updating the tasks. So real world example of long deploy time. That's cool. So, cool. Recommendations for pipeline design. Recommend the following best practices for pipeline design. Okay, super linear. That's cool. Cool. Okay, I think we've succeeded in reading the paper. It's been very enjoyable. I will write a paper review about it. And stay tuned. Until next time.